Hello and welcome back to Civil Field Trainers. So in the previous class, we had carried out the one-way slab design by using Excel sheet. In this class, we'll be carrying out two-way slab design by using Excel sheet. So if I come to the ETABS model over here, and for example, if I'm doing two-way, right? So I have to just come and select a two-way slab in particular. For example, I'm doing this particular slab design. So I have 4.17 and 4.23. Now when it comes to a slab design, you should always make note that the longer side is going to be Ly and the shorter side is going to be Lx. So I'm given the value over here already. For example, if this was 0 and this was 0, what you will basically do is you'll just come pick a slab from here and give the respected values from here into the Excel sheet. Now my Ly is going to be how much? It's going to be the longer side. It's going to be 4.23, and that one is going to be 4.17. Alright, so you take the ETABS and you just input the values from there. The second thing is FCK and F of Y. Again, whatever values you have given, you can take the same values. If I'm going for M20, generally for slab and beam, M20 is what we generally give. So I'll stick with M20. And F of Y, I'm going for 500. Basically, the grade of the steel that I'm using is 500, and the grade of concrete I'm using is M20. Okay. So I'm given all these values. After giving all these values, the very next question comes is what kind of my slab it is. Okay. For example, if I come over here, and if I am say, for example, designing a middle slab somewhere. Okay, for example, if I'm designing this particular slab, so if you can see here, it is continuous on three sides, it is discontinuous on one side. All right, now if I'm coming and designing this particular slab which I am designing, you can see here discontinuous on two sides, it is discontinuous on two sides. Okay, now where will I get all these conditions? For that, you have to come to your code book. If you come to your code book, that is basically IS 456 2000, you have to come to page number 91. If you come to page number 91 to table 26, you can see those same conditions have been given. So we have interior panel here. Okay, interior panel basically means, if I can show it to you in the paint, that if I am having slabs all around, let me just quickly draw this, right? So if I were to draw or design the middle slab, right, this particular slab, if I am trying to design this middle one, so basically what is going to happen is, if I'm designing this particular slab, it is an interior panel, because on all the four sides I have got different slabs, right? Whereas what I'm trying to design is this corner slab. So in the corner slab, what I have, if you see here, if I just open up the conditions, you can see one short edge discontinuous, one long edge discontinuous, all right, two adjacent edges discontinuous, two short edges discontinuous, two long edges discontinuous, three edges discontinuous. Like this, you have got different conditions. So in all these conditions, if you see, two adjacent edges discontinuous is what going to satisfy our current condition. So this edge and this edge adjacent edges are what? They are discontinuous. All right. So I'm going to be selecting this one, two adjacent edges discontinuous, as my slab. So if I come back to my Excel sheet, see here you cannot change anything, but you can change it over here. So I'm giving it what? I'm giving it condition 4. Okay. So automatically it will update from here that two adjacent edges are discontinuous. If you want, you can just pause the video now and you can just read it once. Okay. So one edge is not possible for us. Why? Because here both the sides are discontinuous, right? This side is discontinuous, this side is discontinuous. All right. So keeping that in mind, you have to eliminate things. So first is not possible, second is not possible, third is not possible. Okay. And again, our one short and one long, both of them are discontinuous. So two long edges, we cannot do this, we cannot do this, we cannot do this. So it leaves it with what? It leaves it with the option 4. The two adjacent edges are discontinuous because there are not two short edges discontinuous, right? One is long, which is basically our 4.23 is long and 4.17 is small. So by elimination, okay, the method of elimination, you can say that the fourth condition is going to satisfy my need right now. Okay, the two adjacent edges are discontinuous. So once you do that, all right, so we have done what? We have given the dimensions from our ETABS. We have taken the FCK, we have taken F of Y, whatever you have given there, we have taken it over here. Once you have done that, we have gone ahead to page number 91 in IS 456, page number 91, table number 26. In that table, by the process of elimination, we have decided that fourth is going to be our condition for our given slab. Now, for example, if I were to design, say this slab, right? This slab is basically a two-way slab, but if you see here, three sides is continuous, one side it is discontinuous, right? So for this, what will happen is you will change your condition. So if you see here, like one short is discontinuous, it will come. Okay, so based on the positioning of your slab, your conditions will keep on changing. All right. If you see here, it is basically considered as three-way continuous. One side is discontinuous. So for this, it is completely something different. Okay. So coming back to the code book, sorry, our Excel sheet. So I have taken by the process of elimination from IS 456 page number 91, I have taken my condition as 4. Now, because I have taken my condition as suppose, some few things are going to happen, which we will discuss in a second. But before that, Ly by Lx is going to be 1.02. Basically, it is dividing Ly by Lx. If I just double click over here, you can see the formula, right? So Ly divided by Lx, if I do, I'll get the Ly by Lx value is 1.02. After 1.02, you can see assume D I have given here. What this basically means, I have to give the thickness of my slab. Generally, we give either 4-inch slab or 5-inch slab. Rarely do we go towards 6-inch slab. So I'm sticking with 125 mm. I'm not going more than that. I don't know what kind of a slab I have given here. It's been a long time. Let me just check that 125 mm. Okay, so I've given 125 mm only. So coming back to the Excel sheet, I'm giving 125 mm as my slab. Now for this slab, I have to check my deflection and everything and make sure it is passing or not. So after I've done this, next I have to find what? I have to find the dead weight and everything, right? So I have to find dead load. I've mentioned it separately over here. Dead load of the slab. Let me just paste it over here. Okay. Dead load of the slab, D into 25 is equal to 3.13. 25 is what? Density of RCC. Okay. So D is what? Depth. So it is basically 0.125 times of 25. If you do, you will get the answer as kilonewton per meter square. You get the answer. So this is the dead load. After dead load, we have floor finishes 1.5. Again, you have to come to ETABS, open this up, go for your loads and check what you have given. I have given 1.5 as my floor finish and steel plaster. I have given live as 2. So you just come in, you just upload those same values over here, update those same values over here, and finally you will get a total weight. Please make sure that we have not multiplied 1.5 anywhere. If I double click over here, I've done the summation of this. Right? I have not multiplied 1.5 anywhere. So this is basically our normal loads. They're not factored loads. Okay. So far so good, I believe. Next forward, what we have to do, see whatever values we can take, we have taken it from where? We have taken it from our this one. Let me just make it yellow, so we have a proper understanding of what we are doing. So whatever is yellow, we are basically taking it from where? We are taking it from our this value we have taken from our ETABS, right? So I'll just make them as yellow, so you can understand okay, what are the values I have to take from this one. Again, same thing for this also. I'm taking this value also from my ETABS. So you have to fill in all these values. Automatically, the rest it will calculate. Now, this is the most important part to understand. So I have taken the condition as 4. Now I have to calculate what? My formula. If you come to page number 91 only, you can see the formula is given here. Mx and my formula is given here, for which we have to find alpha x, alpha and alpha y we have to find. Okay. If I just zoom in the formula, you can see, right? Alpha x wl x square, because always be designed for what? Shorter edge. So lx is going to come for both mx and my. But the change is what? The factor. It is going to be alpha x and it's going to be alpha y. So from where will I get alpha x, alpha y? For that, you have to come to the same table. And if you just read the heading over here, short span coefficient alpha x, okay, long span coefficient alpha y. All right. So basically, the Ly by Lx values that you are seeing here, the Ly by Lx here that you're seeing here. Now, based on this Ly by Lx, I am going to get a value from here. Okay. So how does this basically work is like this. So for example, it is, say I'm taking condition 4, right? In condition 4, my Ly by Lx value is say 1.4. So my H condition is 4 and my Ly by Lx value is 1.4, for example, right? For example, if I do this, so I have to come here and I will get this alpha x values from here as 0.071 and 0.053. But what do I get? I have something like 1.02 here. So 1.02, the value 1.02 will come between what? It will come between 1 and 1.1. It is 1.02. It's a second decimal point, right? So 1.0 and then 1.01, 1.02, 1.03, something if you go, you'll get 1.1. Okay. Now generally what we used to do in our classes, we used to do interpolation and we used to carry out the work. But here what we will do is, I have given you a table. Okay, in this table, to every second decimal point, I have given you a value. Okay, so you don't have to do any interpolation at all from your end. Whatever it is directly given here to you. Okay, so what are we going to do now? Automatically it will take everything. So for example, see 1.02, right? 1.02 and the condition is what? My condition is 4. My condition is 4. Let me highlight this. My condition is 4 and my value is 1.02. So value will be what? 0.0482 and 0.036. So if I come here, you can see 0.0482 in the bottom left corner, you can see 0.0482 and 0.0360. 360. Okay. So for example, my Ly by Lx changes now. If I make it 5, for example, if I make it 5, it will become 1.20 and the values automatically will get updated over here. I'll do Control Z. Just keep an eye on these values. Okay. So if I make this as 5, what happens? Automatically based on 1.20, my Ly by Lx value and the kind of condition I have taken, okay, based on this parameter and this parameter, your values will get updated over here automatically. You don't have to do anything. Okay, so instead of doing an interpolation, I have to completely remove that step and I have given you a complete dialog tabular column like this. Okay, it's a very big table. Automatically it will come and take the values for you. Okay, so it is automated process. You don't have to do anything. So coming back here, I think it was 4.23 something. So let me enter that. So I have got my alpha x value and alpha x in negative and positive. So again, this negative and positive, many students get confused. So for this negative moment at continuous edge, positive moment at mid span. So if you come to this one, so this is my slab, right? So basically what is going to happen is my slab is going to end over here. Let me just try to draw this in 3D. Uh, or let me just try to do this. So for example, we have a beam over here, right? And then we'll have one more beam over here. Okay, we'll have one more beam over here, and we'll have one more beam over here. I'm just giving you a example like this. So basically what is going to happen, my whatever rebar is there, it is basically going to end over here, right? It is just going to go and end over there. Let me just change the color to something else. Let me just take a green color. So it is going to go and end over there. Okay, whereas for these two conditions, that is basically my the continuous sides, I'm going to get some more reinforcement here, right? On the top side, negative moment. Okay, so basically the system is telling me, the code book basically is telling me that wherever your beam is ending, the slab is ending over there. Okay, and wherever you beam, after beam you have one more slab, you have a continuous rebar going into that particular slab. So for that I have got two values. All right, so basically I have got negative moment at continuous edge. Okay, negative moment at continuous edge, that's basically what this is going to be, my negative alpha x negative. Okay, and the next thing is basically what, positive moment at mid span they have given me. So they are like, anyhow at your continuous span you're getting the higher value, 1 point something it was, right? Let me just see the values. So 0.0482 at where, at continuous, where I have shown continuous to you. At this place I have shown you continuous, but in the mid span, okay, wherever the values are going to be less, you can see they have given a positive value over there. Basically hogging and sagging moments is what I'm trying to tell you here. Okay, so alpha x you have got for both the continuous span, and for the mid span you have got the values. Now alpha y basically is very simple. All you have to do is come for the ly by lx. Here directly for the fourth one, you can see they have given is a single value, 0.047 and 0.035. Okay, so you come over here, you can come to the alpha y over here, and you can see the values are given to you. Okay, so for the fourth condition, 0.047 and 0.035 is what is given and what we have taken over here. Okay, so for fourth condition, 0.047, 0.035 is directly given to you. You have to take the values directly from here. I hope you have understood. Okay, so whenever we have negatives, basically there we have a continuous slab coming next, right? So you have to give the top reinforcement also, and you have to go over there. In the other place, midspan, they have given the midspan values. All right. Now after doing all of this, again as I had said over here, 6.63 is basically what, 6.63 is my total load. It's not a factored load. So when we come for the moments part, if you see the formula given over here to you, that is alpha x WLX square. Okay, there is no 1.5 multiplication done here, but because we're converting these values to factor, we're multiplying it to 1.5. Okay, so if I just double click over here, you can see they have taken the load, they have taken the value, they have multiplied everything, and they have given you a value. So alpha x negative, that's for continuous. For midspan, again in y direction, continuous and midspan, you have got four values. Okay, if you are confused, let me just try to write something over here like continuous. This is going to be midspan. Okay, again this is going to be continuous, this is going to be midspan. All right, so once this is done, what I have done is I have to check for my required d, how much amount of depth I have provided and how much amount of depth is required. Okay, I have to check that. So for that, there's a formula over here that I have mentioned, and this formula is what I have input over here. Okay, and once you do this, if I double click on this, you can see I have taken what, I have taken the maximum movement. Okay, see 8.33, 8.12, 6.22, 6.05. Okay, so positive two values, negative two values we have. So I have gone for what? Again, we are checking the depth of the slab. So you go for what? You go for the highest value, right? Don't check for the lowest value and say, okay, it is fine for lowest. It is safe. We don't do that. What do we do instead? We go for the highest value and we cross check it with the highest value and see if it is safe or not, right? So if I do this, I'm getting the value, required value of 65. Okay, so D provided is how much? 125, and this is capital D, right? If you know this one, basically if you have the slab which is this thick, what do we have? We have clear cover. After clear cover, we have our rebars also, right? We have clear cover, and then we have our rebar, something like that. It will be sticking like this. Just to control Z, we have our rebars going in the opposite direction, something like this. So what we basically do is, so the whole thing is going to be how much? This is going to be capital D, and this is going to be how much? 125 mm. Yeah. So capital D is equal to 125 mm. Okay. Whereas this part is going to be what? This part is going to be small d, which will be equal to 125 minus the clear coverage I will be giving minus the half the dia which we are considering. Okay. So if you do this, you will get something like 120 mm something you will get. Okay. Half the dia, it is not completely. So 10 divided by 2 we have to do. Okay. If you're considering 10 dia bar. Alright, small d will be equal to cover minus dia divided by 2 is equal to 120 mm. So that's why I've given you a clause over here, change the bar dia accordingly. Now what do I mean by this is, for example, I'm taking 10, right? So I have given 10 over here. If you are taking 8, you have to give 8 over here. Okay, it works like that. So this one part you have to keep an eye on. Now what I'm going to do is, now I know that for my longer side and shorter side, alpha x and alpha y, basically I've got values over here. So in y, highest is 8.12, in x, highest is 8.33. So it's almost the same. I'm going for the highest value now. So in the highest value, basically my moment is 8.33 and my ASC requirement is 202. Okay. Now this 202 value, if you give 10 dia at 389 center to center, it will satisfy this value. Or what you can do, you can give 8 dia at 249 mm center to center, it will satisfy the value. Okay. So for example, what I do, I'll make it as 8. 8 at what I'll do, 8 at, I have to satisfy this value, right? 8 at how much I have to give? I have to give at least 249. I'm going to give 250. Sorry, 240. Yeah, 240 is fine. 240. It will satisfy the whole thing. Okay. So in the longer direction, alpha y, yeah, 8.12 is there. 196 mm is there. Again, I can do. It is asking for 256. I can make it as like something like 250. Okay. If you do this, it should be safe. Okay, so in the x direction, you will provide 8 dia bar at 240 mm center to center. In the long direction, you provide 8 dia at 250 mm center to center based on this values 8.12 and 8.33, because this is going to be our highest moment which we are going to come in our slab. Once you have done this, you have to check for your deflection also. Again, if you see this formula is basically they have reversed engineered this formula to get the PT value. Okay, PT value is required because when check for deflection, you have to go for the PT in the bottom. See percentage tension. Let me just zoom in. Let me just zoom in so that you can see better. Come over here. So because we have the area now, we'll cross multiply it and get the PT out. Okay. So once I've got the PT, this is going to form the bottom line X. All right. And FS we have to calculate. Okay. This lines that is, we have to calculate. FS is basically 0.58 into F of Y divided by area of steel required by area of steel provided. So required is how much you can see here, and how much is provided you have to calculate. Once you have done, you'll get value something like 206 something you will get. Okay. So after doing these two things, they have found the FS, they have found this value. So what that they're going to do, for example, if I get 0.4 and FS has 120, they'll take 0.4, they'll go all the way up to 120 and they'll see what kind of value I'm getting. All right. So if you see modification factor here for my current condition, there is basically 0.21. It's not about 0.4, it's 0.21. And my FS is something like 206 something. So this is 240 is there, 290 is there, somewhere between it will come over here. Okay. So they have gone all the way up and we have got modification factor as 1.99. Again, you don't have to do anything over here. Automatically I have given a command over here, logic command. It will just take it, it will calculate everything on this one, it will just give you a final value like this. Okay. So once you have done all of this, you can come over here and you can see that when it comes for the modification factor, basically L bar D max is equal to L by D into modification factor you have to consider. Once you do a consideration, you'll get something like 52 and effective depth required will be 81. Alright, we just double click this, you can see the values that I have considered. Alright, so whatever this value, it has to be less than 100 mm so it can be safe. Why 100 mm I'm taking? Because if you see here, this is going to be my effective depth. Right, if you see the drawing that I have shown you here, this is going to be my effective depth. So I have made a calculation mistake over here. It's not 120, it has to be 100. Okay, no problem, we'll just erase this off. Can we do it? Yeah. So I have made a mistake over here. right? It's going to be 100 because minus 20 is there, no? I missed that part. So D is effective depth is how much? 100. So effective depth should be satisfied, right? So we come back over here. So this is what the value we'll get. All right. Now if I make some changes, for example, instead of giving 240, I'll give 200. Sorry, I'll give something like 300. Okay. You can see the values changing now. You can see it becomes 99. Now in the acceleration, I'll do the same thing. I'll make it 200, 300. Or if I try to go beyond that, I'll make it 310. You can see it becomes as unsafe. Again, we cannot go 300 and above. For that, I have given you the conditions here. If you're interested, you can just come and refer the conditions along with the code book. Okay, you cannot go beyond these values. You have to take over the lesser of the above three values you have to consider. Okay, so we come over here. Now inside, I'll just go and give it just like 240 or something that we had got. And for this, I think we have got 250. I'll just give this value over here. And the students who already purchased our course, that is basically our ETABS Safe and RCDC course. So you can see there is a coupon code here. That is basically, it expires in 1 or 2 days. All right. So lucky 10 coupon you can apply and you get the entire course over here. And inside this course, you'll get access to this Excel sheet as always. All the Excel sheets are there inside this only. And you don't have to come and request, right? All these Excel sheets you don't have to request separately. Once you have bought the course and I'll share the Excel sheets with you, you can directly download them and edit them. You don't have to request like this separately for, beam, column, slab and everything. Don't do that. Okay, once you have paid and you have got inside the course, directly go and download those things. Once you have downloaded them, you can just go and edit them the way I have shown you. Okay, so I hope you have understood. If there is any mistake in this Excel sheet, please get back to me. I'll try to create an updated version, but I think I have covered everything, almost everything in this given Excel sheet for two-way design. Again, if you want to change the different kind of options, right, you have got approximately 9 different type of two-way slabs, so you can go and select those particular slabs and design accordingly. Okay, so values will vary and you have to keep an eye on them. All right, so with that, I'll wrap up this class. See you guys in the next class. Thank you.